So that's linear models, right? But you can imagine that sometimes these models are not going to represent linear relationships. They're not going to be always a constant rate of change. So let's talk about quadratic a bit. So that's another model. Again, we have lots of different models. But I want to show you this, just a couple examples here. So here's an example where the line, if we try to model this data set with lines, it's not going to quite work. Like, it might sort of work, but it's a little hard, right? And especially if we see this as like a basketball shot, it's definitely not going to be a line, right? And so something like a basketball shot is going to be much better modeled by a quadratic. And this one's a downwards facing quadratic. And so then we can predict things like, will the ball go in or out? So, you know, this is just prompting our sort of thinking around what is a quadratic and how do we graph quadratics, how do we model them? So the most basic form of a quadratic, let's start there, would be like a y or an f of x equals x squared. Like, we've seen the fact that when you have an x squared, you're going to get a quadratic shape, right? Okay, so let's start there because we're going to start with just f of x is x squared. And I want you to give me a bunch of different points. So just write one point that satisfies, one coordinate that would satisfy this function. And I want to get a bunch of different points, right? So what happens if you put a 0 in? What do you get? We have a 0, 0, because 0 squared is 0, right? Then 1 was 1, and 2 was 4. I'm just writing these from the chat. 3 gave us 9. 4 gave us 16. 6 gave us 36. Have we gone the other way at all? 5 gives us 25. That's right. So if somebody can go, because if we only do those numbers that you've given me, I'm not going to get a full picture, right? Okay, nice. 1, 1. And then 2, 4. And 3 is up at 9. So that's as far as I can go. You know, no one's done decimals, right? Like, what's a half? Yeah, a half squared would be a quarter. Like, a third squared would be a ninth. A fifth squared would be a 25th, right? If you think fractions, it's much easier than decimals, I find personally. But yeah, half gives us a quarter. And so you're going to end up getting this sort of, as you get more points in detail, this is a little hard to draw. You're going to get something like that, right? And it keeps going forever and ever. So you've seen something like this. This is a parabola, no big deal. It represents all the possible points that happen when you have an x squared. And there is something really cool here. There is a line of symmetry. You will be asked about that for different parabolas. What is the line of symmetry? Our line of symmetry is the vertical line. A vertical line is always based on what x equals, is at x equals 0 at this point. Okay. Okay, so I'm going to circle a couple points, 0, 0, 1, 1, and 2, 4, and negative 2, 4. Those are the points I'm going to focus on. Because now what I'm going to do is I'm going to change this and say, what if I said I have a g of x, x minus 2. So now I have to think like, I'm going to still be choosing x values to put in so that I can get a table of values so I can graph that. I know that there's an x and there's a square on the x. If I multiply that out, I could get x squared plus 4x plus, or minus 4x plus 4. But I'm just going to keep it the way it is because I think it's easier for me to calculate if I throw in a number the way it is written rather than the expanded form. Okay, so let's do this slowly. So rather than me giving you the x value, I want you to tell me what the x value would be if I wanted my answer to be 0. So what do I put in for x so that my answer is 0? Right, if I put a 2 in, I will get an answer of 0. What would I put in to get an answer of 1? 3. What would I put in to get an answer of 4? 4. What would I put in? Well, there's also the potential of the negative, right? So if I wanted to have this almost that point, so I could put in a 4 minus 2 to get a 4. Is there anything else I could have put in to get still a 4? I think there's 2 options for every answer. 0. Okay, so now I'm going to relate this to the points that I had. What do you notice has happened to my points? How did I get from 0 to 2, and from 1 to 3, and from 2 to 4, and from -2 to 0? Yeah, they're all added by 2. And that's because I had to compensate. I had to add 2 to all my x values in order to produce the same y value because I was getting reduced by -2. You know how if someone's like pulling you back, you have to like work extra hard to still get ahead? It's that same idea of if I know I'm going to lose 2, I now have to put in an extra effort of an extra 2 in the entire time in order to still be producing the same values. I don't know if that kind of works for you, but it's always a little confusing because it says -2, but I'm actually adding 2 to my x. And part of that has to do with, in order for x minus 2 to give me 0, what it would have been for 0, I had to add 2 to both sides in order to figure that out. So instead of being a 0, it has to now be a 2. And same thing, in order for my x minus 2 to be a 1, like it was here, I have to add 2 to compensate. To now it's going to be a 3, and that 3, when I plug it back in, is going to get reduced back by 2, and it's going to give me the same answers as it did for 1 for the regular equation. So let's graph that out, see what happens. 2 is now at 0. 3 is at 1. Sorry, 2 is not right because the scale is throwing me off. 4 is at 4, but it's also at 0, right? And this is probably a point as well. So what happened to my graph? For x minus 2 squared, what happened to the graph in relation to the initial graph that I had? Shifted over by 2 to x. We're moving into transformations, and so this is really important right here, that when you're inside of the x component has -2, remember this happened for circles as well. When we had a circle that had x minus 2 squared plus y minus or plus 3 squared, the center was at 2 positive and 3 negative. It was the opposite for when you had that inside because it shifted from 0, 0, it shifted right to, because it had to compensate for the subtraction of 2, and left or down 3 because it had to compensate for the addition by 3. Okay, so that's one basic of transformations is when you have a shift, like an addition or a subtraction, inside by the variable that is being considered, it's going to act on that variable in your points in an opposite fashion. So let's just pause that and go to Desmos and try that conjecture out. So we'll try a different function like, well, we know what x squared is. So let's just try, what if I type in x minus 5 squared? What's that going to give me once I click that? There's my original. What's going to happen if I do x minus 5 and then squared? Okay, it went to the right by 5. See that? But if I went plus, it's going to go left 5. Okay, so we're just learning how to go left and right now. I could do this with a different function. Let's say I had y equals absolute value of x. That's this function. You could type it in. Absolute value is everything. All the negatives became positive, and so it made a V shape. Now if I go y equals absolute value x minus 5, shifts over to the right by 5. You see that? The nice point to check is always that 0, 0 point. And again, y equals absolute value x plus 5, shifted to the left by 5. Okay. So you have this sort of transformation. Now, maybe I want my model to actually be upside down. So can anyone suggest what I could do to my parabola to flip it so it's downwards facing, not upwards facing? Negative in front of the bracket. If I multiply, so if I have a negative here, what that's doing, like, so if I had done another thing here, so if I had done an h of x is negative x minus 2 squared. Now I'm going to take the same things that I had before for g of x, for that part, but all of my answers, every of these points, all of the answers that normally would have just been these answers are now negated. So it'll be negative 0, negative 1, negative 4, negative 4. Like basically it's just making all of my outputs a negative. And so that's going to basically flip it down. Okay, so we've seen how to move it left and right and possibly upside down, which is very useful for the trajectory of a ball, for instance. But now what if I want to move it up or down? Okay, so what if I want to take my regular f of x and I want to move it up or down? How do I move this back up? Maybe I want to see it a bit higher. So how do I move all these points up by, say, 5? Add on 5. Then let's say FGHI of x, I don't know, so this function of x is now going to be everything I've done before, but then plus 5. So all of these points will now be like added by 5. Because essentially we've taken all that and added 5. So I want to point out 2 things. One is that when you have this general form of a parabola, the parts that are outside of the regular form of the function, right? This was the regular form, bracket squared. Those are affecting the y's. So up by 5, you're just adding 5. You want to do that later because order of operations would get you to multiply first and then add. So literally you can take your regular points, you can multiply them by 2 and then add 5, and that'll transform them the way you need them for the y's. So the y's are acting regularly because they've already been solved from the other side. You know how when we had a circle, like this was still opposite, but it's because it wasn't solved for it, then it was opposite. But since it's been moved over and the y is by itself, these are just acting directly to our answers. Whereas the issue that a lot of people have is that this inside portion is affecting the x's. And it's affecting the x's in an opposite way. So one way to discover that, if you're not sure what to do to your x values, is to set it equal to something like 0 and see what you end up doing when you solve for x. So when you solve, you would add 2 to both sides. So this means that you're going to be adding 2 to all your x values. So you just did it once, and that's all you have to do. Okay. So essentially, this is telling you that you're going right 2. This is telling you what you multiply by. And then this is telling you that you're going up 5. In general, your general parabola form is going to be something like a and x minus h squared and then plus k. And then obviously a can't be 0 because then it zeroes it out and then it's just a line again. So that's your general form. And so h is going to be the side-to-side movement that happens, and it's always opposite. A is going to be the amplification, and K is going to be kind of your up and down. So when you have your regular parabola, there's a bit of an anatomy to it. This point is called the vertex. And so that 0, 0 point is going to be very important because later on it's going to help us understand how to find that vertex, which would potentially ask us to find like what's the maximum possible value or what's the minimum possible value. So based on what we know so far, if it was transformed this way, what would be the vertex based on these variables that we have used here? So this is just a general x squared, but what if I did all this to it? Where would the vertex go? And if that's too hard, what if you had something like x minus 3 squared plus 7? What's the vertex of that? So your x values had to add 3 in order to compensate to be the same thing as what it was when it didn't have that -3 there. And then you added 7, so you went up 7. And so from 0, 0, you went right 3 and up 7. And then if I also made this negative, then this would all be the same, but downwards facing for that. But the vertex would still be at 3, 7. We're going to do another one. So let me give you this one and see if you can figure out and anticipate what this is going to look like. Something squared is our general function, which we know to be a regular parabola. And we also know the domain of f is -infinity to infinity, or all real numbers. The range of f is 0 to infinity. Okay, that's our basic function. And now our new function, right, is going to take our regular table of values and it's going to change it. So I want you to try this on your page as I'm doing it here. Pick a few points, 0, 0, maybe -1, 1, and 2, 4. That'll be enough, and then that'll help me see what's happening. So I just chose this point, and that point. Okay, so what's the first thing we're going to do? So if we want to have x minus 3 squared like that, then it's easiest to keep the answer the same and to shift the x's to match that by adding 3 to them. So I added 3 here. So, right, we're going right by 3. Okay, now think about what you'll do for the next steps. So the next thing that we would do to that bracket, if we're working from inside out, is that -2. So what are we going to do with that? It's multiplying basically the f of x components. So what that's going to do is it's going to multiply. It's going to keep these. It's going to multiply all my y values by -2. So it's actually going to flip my y values over and stretch them to be doubled. So it's actually going to stretch the graph so it looks narrower in the y direction. Right, so these are all going to double. Instead of 4, I'm going to have an 8, but in the other way. So that's going to be way down. So that is a vertical stretch. Okay, and then now finally, just do that in purple. We're going to do the +5 last. So that means we're going to add 5 to all my y values. So it's going to move up by 5. And the reason why this one is particularly important is because we have a whole section on quadratics, and quadratics are actually very useful in applications for us to be able to identify whether there's a maximum or a minimum to our situation. And we saw a couple situations in the past, say like if you're maximizing the volume of a box, or if you're trying to like make the best size chocolate bar, or if you're looking at when sort of the peak of a throw of a ball is. Like there's all these situations, especially in business, where you're interested in either a maximum or a minimum. And quadratics, which are functions with squares in them, are very useful because it's quite easy to find the maximum or the minimum. Okay, so you can also do domain and range. Those have not changed too much, still all real numbers. But now our range is -infinity to, what's this maximum here? Okay, so but the most important part here is this top value. I need that coordinate point. That coordinate point the whole way through is called something special. Does anyone know what that's called? The tip of the parabola, what that's called? Like other than the max. In this case, it's a max, sometimes it's a min. It starts with a V. The vertex. Right, so the vertex is very important. So important that I'm going to make it yellow. So for this function here, this g function, I should be able, if it's in standard form, this is in standard form, when it's all solved like that, I should be able to look at that standard form and know exactly what that vertex is going to be. I didn't even have to do all this transformations or anything. I should be able to know where that vertex is, because the vertex is going to tell me what the maximum or the minimum is. It's going to help me figure out what the range and domain are. It's going to help me with when it's increasing, when it's decreasing, like maybe sometimes you're interested for what interval of x is it increasing, for what interval of x is it decreasing. Vertex is super important. So what's the vertex here? Here, 3, 5, right? If you look at that function that we had, just like, let's just say you only saw this. If you only saw that, could you figure out what the vertex is? Right? You could basically look at this here, because in general, just like for circles, remember we had a center for circles? You've got your HK there, right? Because you're starting with 0, 0, and then you're moving it right by H and up by K. Well, obviously the signs could change, but that's going to leave you with an HK vertex, right? So the vertex in this case, you should be able to see is 3, 5, and in general is HK for something like in general like that. Okay. So that's going to affect your domain and range in general because the vertex is going to help you determine where that range ends off. The domain of a regular parabola is always real, all real numbers. another question they might ask is like, when is it increasing? When is it decreasing? Actually, let's do, is it facing up or down? So what helps us see that? Is it facing up or down? This front number, right? If that front number is negative, in this case, it's facing down, right? So that is told you by A. If A is negative, it's down. And if A is positive, then it hasn't been flipped. So it's still up. So if it's facing down, does it have a max or a min? These are all questions you could be asked. So because it's facing down, it therefore has a maximum. And that means that 5 is the maximum height that it could be at, which then helps you with your domain, which is all real numbers. Your range means that because it's facing down and it reaches up to 5, it's going to be negative infinity to 5. And then sometimes they also ask on what interval is it increasing and on what interval is it decreasing. So for the x, so what x values is the function increasing or decreasing? So all the way up to 3, which is the point where it peaks, it is increasing. So negative infinity to 3 is increasing, and then after 3, it's decreasing. Right? So if I give you another example, right? So let's say this is h of x, the height of some ball is 2 and x minus 6 squared minus 3, right? What's the vertex? Does it open up or down? Does it have a max or min? Right? And then you can ask all those other things. So what's the vertex of this? So 6, negative 3. Remember, the x part is always opposite, and but the y part is not opposite. Not like in circles, they're both opposite. In parabolas, the negative is still there. Yeah, good. Okay, and then is it upwards facing or downwards facing? So which number affects that? That would be the number that multiplies so that the y values switch. Opens up. Yeah, the 2 is the number. This one, I didn't make it negative this time. So that would mean that basically, like if you started with your regular parabola, approximately it would go right 6, down 3, and then it would double. So it'd get narrower. But it didn't multiply by negative, so it didn't drop. Does that make sense? So it opens up, so therefore it has a minimum at 6, negative 3. And then basically what that means is like you found where the minimum amount is, and that's sort of the range of your possibility there. You can answer all the other questions after that as well. Cool, good. Okay, so in the last part of quadratics is then, okay, so it's super easy to identify all the information when it's written in standard form. But what if it's not? And you've done this before, but I want to remind you that sometimes you will have something that is not in standard form. So let's say you had this given to you, right? And you're asked to find the maximum value of this, or something to do with the vertex. There's 2 questions here. One question could be, when are the zeros, which is like x-intercepts, right? I could see this is facing up because the leading coefficient is up. I don't know where the vertex is. I just know that, I don't know, maybe it's like this. I'm totally making it up. Seems like it should have a minimum. Don't know where the vertex is, and it could also have zeros. So the vertex question needs you to put it into standard form, whereas the zeros question might have you factoring it, equaling it to 0, and doing anything we did in the previous module on solving to 0. But right now we're interested in the vertex question. Okay, and so this is a distinction because it looks very similar to the type of question you would have had in the previous unit, but the question was different. The question in the previous unit was asking, when is it equal to 0? We're still kind of interested in that, but we're not focusing on that right now. We're more focused on what is the vertex. And so you might be guessing, well, if we want to have it in this sort of nice format, then we probably need to do something that we've done before when we made the circle equations and then earlier when we did the quadratic formula. Does anyone remember what that's called, that process to make it envelope back into a square? Completing the square, exactly. So the completing the square process is what would bring you back to a format that would help you find H and K. Okay, so let's remind ourselves what the completing the square process would be. Remember, we want to kind of like move this plus 19 over to the side. We want to make sure that our leading coefficient is out. So we want to factor those first two out, the 2 out of the first two things out. So I'm going to have this x squared minus 6x. And then now I'm trying to add something here and subtract it so that this part will be a perfect square. So what do you put there to make that portion be a perfect square? 9, yep. So we're going to add 9. But remember, we can't just add a 9 without subtracting a 9 to compensate, but we don't actually want that minus 9 there. So remember, we had to kick it out. And it's because it's still under the multiplication of 2. So in order for me to get rid of it, it's going to be minus 18 as it's distributed out. And then I just have this part inside, which that is going to be a nice perfect square. And this is going to be put together. 19 minus 18 is plus 1. And so what's my perfect square then? X goes in the first spot. What's that second spot? Yeah, nice. X minus 3, right? Okay, so again, just like we've done before for circles, exactly the same. Now we just have one side to work with because it's a function, but pretty much the exact same process. And once you do that, what that does is that helps you find the vertex as well as the answer to all the other questions. So the vertex based on this is, okay, 3, 1, nice. So it's shifted right 3, up 1, and it's also a doubled shape, which is narrower. Is it facing up or down? You look at the outside number, has it been flipped or not? It's facing up. And so therefore it has a minimum because, sorry, if it's facing up, it's smiling, it has a minimum as well. So the minimum would be a 1 for an x value of 3. If you do this process for the general ax squared plus bx plus c, if you do this exact same process, what you'll find is that the vertex is going to be negative b over 2a. Because if you think of what you end up doing, you end up taking the a out. And then you take half of it, I'm not doing all the parts, and you square it. And what ends up here is b over 2a. And this c is going to be something crazy. So we don't even consider this. It'll just be whatever f of b, negative b over 2a is. And this is a plus here, so that's why this is a minus. So this can help in general if you have a question like this, for instance, and you have your ax squared plus bx plus c, and they're saying, what is the sort of max point, for instance? I don't know what happened there. you could use your negative b over 2a for that. You could say, what's the vertex? And that's going to be negative b over 2a for your x value, and then you can find your y value by plugging it back in instead of trying to have a formula for that. Right, this is the model. They're asking for the amount of time, I think, but let's say we're just interested in this vertex for now. Then you'd say, okay, what's b? What's my a? Right, so whatever, negative 22.9 over 2 times 16, and they're both negative, so it's positive. So you basically would get an x value, and then you could plug it back in and get a y value, and then you could get your vertex. Okay, so in general, that kind of can help you find the vertex if you don't want to, complete the square, but sometimes completing the square is actually, quicker, because then you get the whole thing. You get this whole equation, not just the vertex.